With some delay, I start my presentation, which is the topic and exercise in human-centered AI on Shneiderman's second Copernican revolution. It's joint work with my colleagues Lukas, Annika, and Sven. We will not talk, and we did not investigate, like this talk will not focus on algorithms, but I will focus on methods. I would like to talk about the relationship between humans and AI-powered systems, and this often, when you look at some of the popular movies, end up in some kind of AI meets all human needs utopia, or some dystopia, like you would see in terrifying AI movies. We are interested in the human part of AI, systems that address the needs of real users of humans, systems that in which humans are at the center of system developments, systems for which you have to establish a process that arrives at successful systems. And also systems that are able to explain their actions and that are built with the identified human needs in focus. Shneiderman talks about like the kind of second Copernican revolution, because he says we should get rid of that idea that humans are in the loop around AI algorithms, but we should talk about how systems can be constructed in which AI is in the loop around humans. So we focus on human needs in system development, and therefore I will present some cases from three of our research projects, in which I show you some methods that help us to address human needs in developing AI-powered systems. The first project which I would like to share with you is about understanding human needs in the construction of clinical decision support systems. It's joint work with the colleagues at the WTH Aachen, where we are interested in developing an AI-based decision support systems that is used in intensive care units, where we focus on the area of volume therapy, and in which we do not just take AI algorithms to see how we can support physicians and nurses in emergency units better, but we try first to understand by observing potential users, understanding the context, interviewing in which they are working, understanding their needs, to make sure that we have a clear idea what would support them best. I can't share photos that we, of course, also did at the TriRhenaTec Berlin, but I can show you some of the artifacts that we used. We did interviews, we did like very detailed observations. We became part of the context for which we are developing the system, and we tried to create scenarios. We even did some kind of very raw comic strips to outline the typical scenarios in which the users are acting. And to give you an idea how detailed our analysis was, I can share some of the user journeys that we created. Here you see like the user journeys for two of our personas that we addressed, namely the nurse, the ICU nurse Peter, and the resident Hannah, where we tried to understand by talking to them, by observing them, by becoming part of their daily life, to understand their needs. And this is just a very coarse description. The full detail is shown here. They really took a very, very deep dive into the respective professional lives of these users to understand their needs in order to derive system requirements. So we focused on their motives, on their goals, and also on their motor actions, to make sure that we have a clear picture of how they would, which kind of system they would need, and also to get an understanding about like potential acceptance barriers. So we are following the approach that Mark Hassenzahl developed, which focuses on well-being as a design goal. And in fact, we try to make sure that we have an overall idea about the psychological needs that these users that we try to support with an AI-based decision support method support system actually have. So algorithms are just our tools that we use to address the needs of real users. In this case, I like to focus on the empirical work that is strictly necessary in order to make sure that we do not just develop a system that is of no real use because it fails to address the needs. We don't have the time to actually dive into a demo of the system, but if you are interested, I would like to refer to the paper that we recently published. We have two, one presented at the Kai and the other at the Designing Interactive Systems. So here we saw that we use like empirical methods to understand the needs. In the second example, which is about autonomous mobility on demand systems, we try to understand what motivates people to use autonomous vehicles to make sure that they arrive at a specific destination, while having in mind that other passengers might enter the same system that they are using. So we are talking about like systems that are completely autonomous and that can be called via your smartphone. In order to understand the potential assumptions of users, we did a lot of empirical work. We did like large-scale interviews. We tried to make sure to talk with potential passengers. We did like a lot of prototyping to understand what would be a potential barrier that prevents you from using such a system. Potential acceptance barriers include, they are quite well investigated in the literature, but we try to make sure that we understand these in order to address these barriers as early as possible in system development. So we would like to build a system, we would like to build the right system, and to inform system design, we used a lot of prototyping, and it's quite hard to build a prototype of an autonomous vehicle. And we used like very simple methods. What you see here is one of our approaches. We used a very, very simple video-based simulator in various variants, and we also integrated like actors that played the role of potential passengers that enter the respective autonomous shuttle. In fact, this helped us a lot to understand the information requirements of potential users. It helped us to understand what we should show the users in such a situation where no driver is, that you might have asked if he or she would be available in a car that will be driven by a real human. These simulators are extremely easy to create, but they help to understand and to mimic the situation. In fact, we can show that there's a very high feeling of reality, and we now have like several variants of those very simple simulation systems that really provides the input that we need to address the right needs of users. We have also published a paper on designing interactive systems, and we are just about to use like Wizard of Oz studies where we are using like real cars in real traffic, but of course this is a Wizard of Oz study, which means that this car is driven by a human, but potential users have the feeling, or they should not know, that in fact there's a driver sitting in front of the car. This allows us, these very simple techniques allow us to understand the needs of users, and they also allow us to understand the requirements of an interface, whether we should use like a conversational interface or a GUI. And these are the variants that we are actually exploring using such Wizard of Oz techniques. We just presented a paper at Mobile HCI, which we outlined our results. It's a very, very cheap and highly informative way, and it's also immersive methods to do some kind of context-based prototyping. And it also helps us to understand like the role of other passengers and also the information needs that users have when using shared autonomous vehicles. The final example that I would like to share addresses like two core questions. Prototyping is something that is at the center of user experience design. We are constantly working with prototypes, and in this case we are using AI-based technique to emulate like synthetic users and to create an application that helps us to predict human performance. So when I said that when we are using prototypes all the time, you see an example here that is taken from another project where we did like paper prototyping, then like a very simple photo-based interactive systems, then like wireframes, and then like a full-fledged high-fidelity prototype. We create our own prototyping tool called Untitled AI, which we just released in the startup that we founded. And the interesting thing with this prototyping tool is that you cannot just create interactive prototypes, but you can also simulate the interaction of synthetic humans with a future interface. So we base this system on the ACT-R cognitive architecture, which is a hybrid architecture consisting of a symbolic layer that is supported by an activation-based sub-symbolic layer. And this AI-based component allows us to create artificial users that interact with the very same interface that human users would interact with. So they perceive the elements on the screen. They have like a procedural and declarative memory. They learn the consequences or actions, and they also get to speed when using the system. And they also like can click on the screen. They can use the mouse just as humans do. And it's a zero-parameter model because all of the relevant information has been taken from the ACT-R literature, which is some kind of like condensed parameter set taken from cognitive psychology. It's very easy to apply this model. You just have like the ACT-R cognitive architecture. You have a generated model. I will show you how these models are generated, and then you need a prototype in order to create predictions. What you essentially do as a designer is you create a prototype, and then you demonstrate like a typical interaction path while the model is watching you, while the system is watching you, and it creates a simple cognitive model that you can then run multiple times in order to create a learning history and to derive predictions. Sounds very theoretical, but I will show you an example from a real-world revetting machine. That's a kind of machine that you need when you build like the wings of a plane. And what you see here is like this model in action. It actually shows you like the attentional moves. It also shows you like the motor action of the system, so we can really observe a synthetic user in action, and it will help us to create a synthetic population. Of course, that would be quite useless if the prediction would be quite far off. We have used that in quite many domains now, and you can see that you can approximate like the learning trajectories of users, and it has this. There are still open questions involved, and it really works when you have like a routine behavior in focus. It will not learn a system that you have to explore in total, but it opens up new possibilities for designers because you can explore the consequences of your design decisions in a second. Just to give you an idea, we created a model of a Chinese app called QQ Music, which is something like Spotify, and we also created a prototype of an optimized version of Spotify. And we then let the model run on each of these interfaces, so we can really see how the model would improve performance over time, so we can actually see the quantitative consequences of user behavior that are related to our design decisions, which allows us to actually predict the performance over time. And this is exactly what we did for these three prototypes, where we see, okay, our Spotify redesign is indeed better than the original one, and it's far better than the Chinese QQ Music one. We wrote a paper about this, and we also, in which we also discussed like the limits of such models, which are essentially based on so-called GOMS models of routine behavior. So we call this approach predictive prototyping because it allows us to derive quantitative performance data for real life routine tasks based on this cognitive architecture. The cognitive architecture was created by John Anderson's group more than 30 years ago, and it's really grounded in a very broad set of empirical data. So we cannot just create behavior, but we can also derive like performance predictions, and we can address like group learning, which is something that's very hard to investigate in the lab, because if you're doing like usability tests, you will never see learning in a broader sense, because you typically have a very small subset, a very small sample size, and you also typically present one task for one time, so there's hardly scientific data available to explore learning. It's low effort because you have to do the prototype anyway, and the only thing that you have to essentially to do on top of that is to demonstrate like a typical interaction path. And it essentially allows us to iterate like design alternatives and then compare the respective implications. My goal with this talk was to show that there's more to AI than just algorithms, but that we really should focus on the human side, that we really should understand the needs of users, and there's a broad range of methods available in user experience design to understand the needs and to create trustworthy AI-based system. And we can also evaluate the context much earlier than just after some progress in implementation has been made. And we can also create tools. There's now a growing community that is has very strong interest in the creation of human-centered AI systems. At the University of Applied Sciences in Kaiserslautern, we have a competence center on usability and user experience, in which we address questions that concern the relationship between humans and machines. Thank you very much for your attention.